Okay, so we're going to be talking about simple harmonic motion. And what exactly is that? Well, harmonic motion is, if you think about it, we've got waves, sound travels in waves, and if you think about a sine curve, it kind of travels like this. It's always kind of directed towards an equilibrium position. Okay, you also have springs, when you pull a spring and then it expands and then it collapses back, so it's moving back towards its equilibrium position. So we can model that using some trigonometric functions, and that's exactly what we're going to do today. So the first question here says, write the equations that describe the simple harmonic motion of a particle moving uniformly around a circle of radius 9 units with a linear speed of 6 units per second. So let's take a look at this right here. And we've got the position of a point oscillating about an equilibrium position at time t, modeled by either of these two functions. First we have a cosine omega t, and then we have a sine omega t. A and omega are constants, and omega has to be positive. The amplitude, of course, of the motion is absolute value of a. The period will be 2 pi over omega. Frequency, of course, will be the reciprocal, which is omega over 2 pi oscillations per time unit. Okay, so we're going to take a look at this and we're going to try to decipher what this may mean. And it's actually not that difficult. Okay, so first thing we need to do is write down what it is that we know. We know for sure the first fact that they gave us is that the radius is 9 units. All right, so 9 units. All right, and then we also know a linear speed that they gave us, linear speed, and that is going to be 6 units per second. Okay, so 6 units per second. I'm going to write that down. I've got that information there. And now all I need to do is think about the equations in terms of the x and the y component. Well, the x will follow the cosine, the y will follow the sine, just as it is when you're talking about sines and cosines. Let's take a look at this one. The formula for x will be, let's see, s of t equals a cosine omega t, and the formula here for the equation for y, s of t will be a sine omega t. Okay, now all we do is we fill in what it is that we know. Well, this right here corresponds to a, our amplitude, and this here corresponds to our omega. So all that we have to do along the x component rather is to fill in what we know. X equal 9 cosine, omega being 6, so 6t. So this is the equation along the x component of our oscillation here. And then the y component will be the same thing except sine, 9 sine of 6t. So this right here is the y component of this particle moving around this circle. And it can be modeled with either of these two equations here. But this is what we mean when we say we're talking about simple harmonic motion. So go ahead and look through these again. This right here, again, 2 pi over omega. In this case, if you think about the period, and I guess I could jot that down for you, the period would be 2 pi over 6. So 2 pi over 6 would be what? Pi over 3. So this is the period. And if you think about the frequency, well, the frequency is simply the reciprocal. So the frequency would be then 3 over pi. So this is how many oscillations it would actually complete. So what we've done here in effect is we have reduced the period from the original, which the original period being 2 pi. And then since we've reduced the period, we've actually increased the frequency. So let's write that down as well. That's an important fact. We have reduced the period and we have increased the frequency. They are inversely proportional. So what that means is that when you shorten the period, you've actually allowed for it to loop back and forth more times. So it's going to complete more oscillations in the amount of time that you've allotted. So that's just a little discussion on simple harmonic motion and, of course, period and frequency.